give the seminar talk, but now we have to work how we have to work. So I'm going to speak about manifold learning and how these concepts are applied in inverse problems for wave equation. And first part of the talk is done in collaboration with Charles Fefferman, Sergei Ivanov, Yaroslav Kurylev, and Narayanan. And then the applications to inverse problems are done together with Roberta Bosi and Yaroslav Kurylev, and also some other co-authors that I mentioned separately. So first I will start about the manifold learning problem. In particular, I'm going to discuss two problems. One is how to learn an embedded submanifold in RD. And then we apply these results to learning abstract manifolds. And also I know that in your institute there are also computer scientists, so I emphasize some construction algorithms. And finally, I will tell how these are related to wave imaging and problems encountered in applications in earth sciences and in medical imaging. So let us start from these two problems that we study. The first problem that we could call surface learning, that is more often also known just generally as manifold learning, that actually means constructing an embedded submanifold from sample points. So we have a submanifold of dimension n in large dimensional space Rd, and we are given a discrete set of points, typically.
Matti, the slides are not moving for me.
Ah, okay, sorry. Okay, let's maybe, are they moving now?
Yes.
Okay, thank you very much, yes, great. So this is the outline. Let's start with learning embedded submanifolds and also the general theme, what type of problems we study. So the first problem that we study is to find a smooth embedded manifold in Euclidean space when we are given a set of points that are close to this surface. So we are given data points set X, that typically is a discrete set. In applications, that is just called a point cloud. And the dimension of the ambient space is D, so that's very large. And there may be some small dimensional submanifold of dimension n. And our aim is to construct a smooth surface that has dimension n that approximates these data points, so that the curvature of the surface is bounded, and the Hausdorff distance that I define also soon is more that measures the distance of the data points and the smooth surface. So in numerical tests, one often uses this type of Swiss roll surface that is here, that contains points. In practical applications, you could have some object, and you know lots of points on this on the surface of this object, and then you want to draw a smooth surface that interprets these points. For instance, here in Finland, we use this to laser imaging of forests, where by using laser we find lots of dots on surfaces of trees, and then we want to model the trees and the forests. And typically, in most applications, actually, this D is very large dimensional space. So this is the first type of problems that we consider. The other problem is more invariant. It is a construction of a manifold from discrete data. And by this discrete data, I mean that we have a discrete metric space, X, and then we have a distance function on this metric space. And then we want to find some Riemannian manifold with Riemannian metric, so that the discrete metric space and the Riemannian manifold are also almost isometric. I will define these concepts a little bit later. We require that the manifold is smooth in the sense that the curvature is bounded, and also the injectivity radius is bounded. The injectivity radius is the radius of polar coordinates. So that if you take arbitrary point on the manifold, then you want to use local coordinates in a ball that has radius r. And if and the injectivity radius is infimum of all radiuses where the Riemannian polar coordinates or normal coordinates are well defined. And here I emphasize that we are trying to learn abstract manifold from abstract metric space. So this is not embedded to any ambient space, but we are interested of learning the intrinsic metric on the manifold. So these are the two problems that we are going to consider.
So you want the injectivity radius bounded below, I guess?
So we want that the curvature is bounded both from above and below.
Oh, okay.
Yes, so we want to have two-sided estimates. Thank you for the question. That's actually very essential. It will be very interesting to consider only one-dimensional, one-directional bounds for the curvature.
No, I meant the injectivity radius.
For the injectivity radius, we want that it is bounded from below.
Okay.
Yes, that's what we want. Thank you. So what type of problems are such that we encounter this abstract manifold learning problem when we are not looking for embedded submanifolds? In applications, one example comes from considering travel time distances. For instance, when one measures travel times of earthquakes, the earthquakes have so-called body waves that propagate through the earth, but also there are surface waves that propagate along the surface. And actually these surface waves typically are very strong because they decay along two-dimensional surface. So they decay relatively slowly. So they are very important. And these surface waves, they propagate close to the surface of the earth. So we could consider surface of earth through two-dimensional sphere as a manifold. Then we have lots of sample points. We have earthquake sources and then measurements where when the earth surface waves arrive to different points of the earth, on the surface of earth, and then we would like to reconstruct the Riemannian metric that corresponds to travel time metric. And here is, for instance, a reconstruction from earthquake data, how the earth scientists believe that the wave speed of surface waves, how it behaves a little bit below the surface of Earth. So here we don't have embedded submanifold. We have abstract manifold, surface of Earth, and on surface of manifold, surface of Earth, we have a Riemannian metric that models the travel time of earthquakes. It's not the Euclidean metric, but it's related to speed of earthquake waves, and that is related to materials that are below the surface of the Earth. So this is the abstract problem. That is one example. Okay, let's go to particular problems. Let us start from learning an embedded submanifold in RD. And I recall here was the copy of the earlier slides. So we have a point cloud, just points in Euclidean space of dimension d, and we want to approximate this data set with n-dimensional smooth surface. This is our task. And we are going to measure the error of the data set in the smooth surface using the Hausdorff metric. Let me recall the definition of this. So when we have any metric space Y, then we define the Hausdorff distance to subsets A and B. Actually, to make this distance really distance, so that the two objects are the same if they have distance 0, one should assume that these sets are at least closed. Typically, we consider a compact metric space Y. So the Hausdorff distance is defined between these two sets A and B. That is the maximum of two functions. This first function here is the maximal distance of points in A to all points of set B. And then we have the symmetric supremum where roles on A and B are changed. So we are like in this picture, if we have these two sets, the Hausdorff distance is realized by this arrow that measures the point of the distance of the point here that is very far away to the other set. This is how we measure the distances of sets. And when we have a metric space Y and subset A, we consider also epsilon neighborhoods of the set. So epsilon neighborhood of the set is here defined here. It consists of all points of Y such that the distance of Y to set A is smaller than epsilon. And I systematically use this term that we say that subset A is epsilon dense in metric space Y if its epsilon neighborhood is the whole space. These are the concepts that we are using. So how to test if some point cloud is such that there is some smooth manifold that approximates it. So let's E with the Euclidean space be here RD, and I use this notation that bore we have considered bores with radius R and center X. Then we have a subset of the Euclidean space X. We specify the dimension n, and then two parameters R and delta. We say that the subset X is delta close to n flats at scale R if the following is true. We take any point X in our dataset, and then near it we consider an affine n-dimensional space. So like in this picture, we could take here one point, and then we could take an affine space. And then we consider the intersection of our dataset X with r-dimensional bore, and then the intersection of the plane, of the affine space, and the same r-dimensional bore. And we require that the Hausdorff distance of these sets is smaller than delta. So this here is just the bore of the affine space. Here we have a bore. We could think this is so all points in r-dimensional bore. So so we take like arbitrary points, then we consider bores of radius R, and we ask, can we approximate the set in Hausdorff sense with bore disks that are intersections of affine space and bores. And if we originally have a smooth surface in RD, then it is possible by using local tangent spaces to approximate the surface with delta. Actually, so the smooth surface using this definition is delta close to n flats when delta has the value some constant that is related to the second fundamental form times r squared. So this is the definition of how we have a test if the set is locally close to affine spaces. And our first result with Fefferman, Ivanov, Kurylev, and Narayanan, this was the date when the paper came online, is the following, that actually we could consider also infinite dimensional spaces. So if we have a separable Hilbert space, but typically in applications this is just RD, then we specify the dimension, then the scale R, and then the error parameter delta has to be small enough. Then if we have some subset of the Euclidean space that is delta close to n flats at scale R, then it's possible to construct or close it, or if the surface is bounded, or complete if it's unbounded, n-dimensional smooth submanifold such that the Hausdorff distance of the dataset to the smooth surface is smaller than 5 times delta. Then the second fundamental form, that is practically the same thing as the curvature of this surface, is everywhere bounded by constant times this quantity delta to times r to -2, and also the injectivity radius can be bounded. So let's first look when this result is useful. This result is useful when this curvature bound, the second fundamental form, is bounded by some finite number. So this requires that delta is smaller than constant times r squared. Then the surface has bounded curvature. And I recall from here that any surface actually is closed to, is CR2 close to n flats at scale r. So this actually says that this result up to constant value of constants is optimal. So let me explain also how this is done constructively, and later we will apply
What
this.
What is the normal injectivity radius?
So, sorry, yes, I forgot to mention this. This is that when we have a surface in Euclidean space, then we are considering the tubular neighborhood. So we want to we consider all points that. So okay, the rigorous definition is that if we have a point that is closer to M than this normal injectivity radius, then it has the unique closest point to the surface.
Okay,
so basically, this means that there is a tubular neighborhood of radius r/3 that we can draw around the surface, and in this tubular neighborhood we have nice coordinates.
thank you.
Thank you very much. So let's look the constructive algorithm, how this is done. It also indicates the ideas of the proof. So what we will do is that we take these black points here. Those are the data points, and then we look its neighborhood. These blue lines, blue curves here model the boundary of the neighborhoods, neighborhood of some R neighborhood of these points. Then we are going to locally squeeze it. I define this in a second, and I squeeze it in different places, and finally I obtain a smooth surface. So let's look the details of this construction. So for simplifying notation, let's assume this scale that we consider R is equal to 1, and we assume that this data set that is given to us is finite. And to use this algorithm, we assume that the data set is actually delta close to n flats at scale R. So it can be locally approximated with affine planes. So how we do this construction? We take first we define a coarse net in the data set. So we take a maximal set of points where all points are separated by 100. So the mutual distances of all points are at least 100. So we take a coarse net. Then for all points in this coarse net, we know that there are some affine subspaces, so that the locally in the ball of radius 1, centered at the point Qi in this coarse net, X is close to this affine plane. And let Pi denote the orthogonal projectors onto these affine spaces. So let's go here in this picture. We assume that there is for this affine plane around this area, there is some affine plane that approximates this reasonably well. Then we make a combination of orthogonal projector and the identity map. And how we do this? We take a smooth cutoff function, psi, that is close to 1, near 0. And then we define local squeezing map. That is a convex combination with, we have the, let's see, convex combination of the orthogonal projector to affine space and to identity map. And here we have this, the weight in this convex combination is a smooth bump-off function, that is this cutoff function psi evaluated at the distance from x to this point Qi, that is we consider as origin. So this phi I map, this is here, this is this, we do a local squeeze. So here, in this region, near this region, the phi I is just orthogonal projector. Then it smoothly is transformed to identity map. So here the map is identity map. Here it squeezes the manifold, here it keeps the same. So we do squeezing here by using one of these maps. Then we take other local squeezing map, squeeze the set here. Then we take a squeezing map in this area, squeeze it in this way. And when we squeeze it everywhere, we obtain a smooth. Then we have squeezed the manifold everywhere. So how we do? We have these local squeezing maps. Let's combine all of them. And then we take the delta neighborhood of the whole data set and squeeze it. And then it turns out that this obtained image, this is a smooth n-dimensional surface that we wanted to construct. And this has the required properties. So this gives a theorem here, gives a criteria and the construction how a point cloud in Euclidean space can be approximated with a smooth submanifold.
Is this a retraction onto M?
Sorry? Can you repeat?
Is this the composite map a retraction onto M?
No, it is not. No, it is not construction. But if you go very far away, then it's just an identity map. And locally, so in this area,
okay.
But
I see. Okay. So the image is okay. But maybe in a neighborhood, in the tubular neighborhood that you spoke of, does this retract to M?
Let's see. I think that then I don't think so, because if you think of a sphere, then the projector to the sphere from inside like extends distances.
Okay.
But it has bounded biellipse. It's biellipsic.
The question was a retraction, not a contraction, I think. No?
Well, it's clear it's not a retraction because the map acts as identity far away. So then you can ask, okay, the question is, on points of M, does it act as identity? Even that's not true, right?
Yes, I think it's not true.
Yeah. Thank you.
Thank you very much. So let's apply this then to the abstract manifold problem, and where we don't have any embedded spaces. And then later we apply this for inverse problems. Okay, so this was recalling of one of the earlier slides. So our task is that we are given a metric space. In applications, I would say that it is discrete metric space, but that's not really necessary. Then we want to find out, we want to construct a smooth Riemannian manifold, so that the smooth Riemannian manifold is almost isometric. And then we want to bound the curvature and the injectivity radius from below. That's what we want to do. So the final product that we construct, it is not the manifold that is embedded in RD, but it is just, of course, any manifold can be embedded to Euclidean space, but it has some intrinsic metric that we want to construct. So let us again start with some concepts that we need. Now, when we speak about abstract metric spaces, we have to compare them. So let us assume that we have two compact metric spaces, X and Y. And then there's a fancy definition of Gromov-Hausdorff distance that is such that we take infimum over all metric spaces Z, such that both spaces X and Y, they can be isometrically embedded to the larger metric space Z. And in this metric space Z, we have well-defined Hausdorff distance. And the infimum of all these Hausdorff distances over the larger metric spaces Z, that is the Gromov-Hausdorff distance. So it looks very nice. There's also a practical definition that gives equivalent metric. And this metric is defined as follows. That we say that the Gromov-Hausdorff distance of two metric spaces is infimum of all epsilon, such that the following is true. So we take epsilon dense sequences, subsets in the metric spaces. For instance, here if they have one metric space and here other, we take these red points and blue points. And then we number them so that we know what is the number of this point. This is point 1, here is corresponding point 1, here is, for instance, corresponding point number 2 and 3, and here is 2 and 3. And then we compare the distances between these red points and the corresponding blue points. And if the distances of the points having the same numbers, if this distance is in this picture and these distances are the same up to error epsilon, then we think that this is acceptable epsilon, and then we take infimum of all acceptable epsilons. And this is a practical way of, because this does not need any external metric spaces. So this is a practical way of thinking the Gromov-Hausdorff metrics, and it gives the distance for two compact metric spaces, how close to these things are to each other.
So your practical definition is not just a heuristic; it's an actual way to calculate the Gromov-Hausdorff distance. Is that what you're saying?
That is true. Yes. So this is. I would say that this computation takes. It may be computationally challenging because you have to order the points in same way. But actually, unfortunately, I'm not the expert on this very topic. But this is constructive way to this you could in principle at least with the NP hard algorithm you can find what is the estimate this Gromov-Hausdorff distance.
Thank you.
Yeah, it is constructive. So now this was the question. We want to construct an abstract manifold, and for that we need that this data set, this data metric space, satisfies two conditions: a local condition and a global condition. And let me go through those. First, the local condition. We want to say that the metric space X that is given to us that locally approximates a Euclidean space. So here is the definition. We say that the metric space X is delta close to a Euclidean space Rd at scale R. So delta and R are just here some parameters. If it holds that, if you look we take any point X in the data set, the data metric space, and then we consider the ball of radius R in the data space in the data space that is given to us. Then we consider ball of radius R in Euclidean space. If the Gromov-Hausdorff distance of these two balls is smaller than delta, this holds for all X, then we say that this metric space X is delta close to Rn at scale R. And actually, any smooth manifold is C times R to power 3 close to Rn at scale R. The reason for this is that we can take the tangent space of the abstract Riemannian manifold, and when we consider the exponential map that is given by the geodesics. So the ball in the tangent space and the ball on the abstract manifold, they actually are very close to each other when R is small. So this is the local condition. And let me now then go to the global condition. So okay, so the global condition is the following: that imitates that any two points can be connected with the geodesic. Now we do this in discrete space. So we say that in the metric space X, the sequence of points is delta J if every point to the next point has distance less than delta. So we have the jump from one point to other with small steps at time, steps that has smaller size than delta. Then we have other definition. We say that the sequence is delta straight, so it's almost like a straight line or almost like as a geodesic. If it holds that this inequality is valid. So what this inequality says, if we want to consider this, if xi is here and xk is here, so we consider this distance, then this distance from xi to this last point here, this satisfies that if we go first from this point to any of the middle points and then from middle points to the end, then this distance plus this distance is smaller than this whole distance plus delta. So that of course we have the triangular inequality, and this says that the opposite inequality is valid with small error. If we would have a line in Euclidean space and we take points from that, then this condition would be valid. So this basically is a condition that this sequence is the shortest possible route, and something happened. Shortest possible route, and that when you step at the middle points, then we make a small error in total distance that we want to travel. Then we say that that the discrete metric space X is delta intrinsic if any 2 points on it can be connected with delta straight delta chain that starts from point X and ends to point Y. So this is the analog of the Hopf-Riemann theorem. Hopf-Riemann theorem says that any 2 points on Riemannian manifold that is complete can be connected with the geodesic, that is shortest path between these 2 points. And so this says that there's a discrete set of points that imitate a straight line between these 2 points. Now we have tools enough to formulate the main theorem for abstract manifolds that we did with Fefferman, Ivanov, Kurylev, and Narayanan. And it says the following. If we have a metric space that is given to us that has bounded diameter, we specify the dimension and scale that we are considering. And then we consider error parameter delta, that is just small enough. Then if the metric space X is delta intrinsic, so it satisfies the global condition, and it is delta close to Rn at scale R, so it satisfies the local condition, then there exists a compact n-dimensional Riemannian manifold that is such that we have to estimate that how large is the Gromov-Hausdorff distance of the data metric space and the constructed manifold. And the sectional curvature of the manifold is also bounded by this quantity, delta r to the power minus 3. And the injectivity radius is also bounded by r over 2. This can be actually improved, but I don't go to that in this context. So when this result is useful, this result is interesting when delta is smaller than constant times to r to the power 3, because then this curvature bound says that the sectional curvature is bounded. Also in this case, this Gromov-Hausdorff distance is bounded by power of delta. And what else? So we had this result here, for instance, that actually if you a priori have some smooth manifold, then it is delta close to Rn at scale R when delta is constant times R to the power 3. So its power is here the same. So this means that this is also optimal result up to values of constants. So this is relatively abstract. Of course, it is nice because it somehow works with arbitrary metric space, but how we use this in applications, especially for imaging. Here we have a corollary. So let's assume that we a priori have some compact n-dimensional manifold that has a bounded curvature. Sectional curvature is bounded. Then we choose parameter r that is small enough, depending on n and curvature k, and consider error parameter that is curvature times r to power curvature bound times r to power 3. And then we assume something mild for the injectivity radius. Let's now assume that we are given a delta dense subset of the manifold that we want to study, and we also know the approximative distance function. And the approximative distance function is such that for small distances, it is close to the true distance up to error delta, and for large distances, it can be actually anything. It's just something. It's big enough. Then, given this set X, the discrete set X, and the approximative metric delta tilde on it, we can construct a compact, smooth Riemannian manifold with a metric G on it. such that there exists some diffeomorphism from the constructed set to the original set, so that we have this type of bi-Lipschitz inequality for the distances. So distances are the ratio of distances is bounded by L, 1 over L, where L is 1 plus something small. And also the sectional curvature is bounded by the original sectional curvature bound times some constant depending on the dimension. And also the injective radius of the contractile manifold is close to that of N. And I don't explain this so because it's technical, but we don't lose the injectivity radius comes only slightly smaller, or it is relatively small, large anyway. And I mentioned that here we consider small deterministic errors. Recently with Fefferman, Ivanov, and Narayanan, we have extensions of this result when we assume that this approximative distance function is given by relatively large Gaussian errors, but then we have to have lots of points that we sample from the smooth manifold. Okay, let me explain the construction of this. So here is a schematic picture. These red points are the data set, the metric space that is given to us. Then we will separate it to balls. Balls are mapped to Euclidean space. The Euclidean space is then embedded to some larger dimensional Euclidean space, and then we do interpolation. Let me explain the details of this construction. Again, we assume for simplicity that the scale that we consider R is equal to 1, and we are given the finite metric space X. So how we do? As earlier, we again start with the coarse net. We take a maximal subset where all points have distances at least 100, 1 over 100. So we take this is maximal 100 separated set. I call this coarse net. And then we, for each point in this coarse net, we introduce a ball in n-dimensional Euclidean space. I call these disks, and let's think them as two-dimensional disks. That's at least how I think those. That is such that for every point in this coordinate, we know by the assumptions of the theorem that there is some almost isometric map from the ball of the metric space centered at Qi to the balls in the Euclidean space, to these disks. So this is isometry up to error delta. So let's look at the picture. Here we have the balls of the original metric space. Then we embed them to disks in Euclidean space. And we are, in particular, we are interested in what happens when two disks, when two balls here intersect. What happens for these disks? Because we think these disks as local coordinates. Okay, what we do? So if we have 2 points, Qi and Qj in the coordinate that are close to each other, then we consider these disks as local coordinates, and we construct affine transition maps between these local coordinate charge. So there are some affine maps so that these isometries satisfy this inequality for all points in this intersection of the poles. So here in the intersection, when we map them to the coordinate charge, then we have affine transition maps between the charge. So we are building the core manifold from local coordinate charge. Okay, what we do next? We take omega, that is union of all these disks, and then by using a smooth cutoff function, that is 1 near 0, we define local embeddings. We define maps Fj that map all disks to Rn plus 1 as follows. That the point x in this union omega, we know that it belongs in some disk di. So we take the map, use this affine map to map it Rn, And then we multiply it with a smooth cutoff function, which actually tells that if this embedding makes any sense or it doesn't. So if this if the point x is in di, where the index I satisfies this property, so that the affine maps make sense, then and this is maybe close to 1. We take this affine map multiplied by the cutoff function, and then we add to this sequence the knowledge if this affine function, this cutoff function has value 0 or if that is positive. So these are local embeddings. Then we imitate from differential geometry.
Excuse me, what are the yi's?
Sorry.
Arbitrary?
Yes, sorry. Oh gosh, the yi is the yes, the yi's are the centers of these disks.
Yeah, y is the center of di, but the arbitrary points of Rn, they are not at all related to anything.
We just choose this yi so that all these disks becomes disjoint.
I see. Okay.
Yeah, but excellent question. Very amazing how rapidly you are looking at the algorithm.
Okay.
Thank you very much. So we have this local embeddings. This is very cool embedding in the disk dj. Then we imitate the Whitney embedding from differential geometry. We just make a sequence where all these embeddings are put into the sequence, and this maps the union of all disks to Euclidean space that has relatively large dimension. There are ways to reduce this dimension, but I don't go to that. And then we denote by sigma j's are the images of the disks in this embedding. Let's go back to the picture, what we have done. We have taken here the balls of the discrete metric space, then we embed those to Euclidean space to disjoint balls and call those disks. Then all these disks are embedded to Euclidean. This area here is in the Euclidean space of dimension, the relatively large dimension, this space E. We embed all these disks to these blue sets that I denote by sigma j. And this embedding is constructed actually in such a way that these two balls that intersect. When I embed them first to disks and then I embed those to Euclidean space, then this blue curve here coming from this ball and this blue curve coming from this, they are here almost intersecting. They are quite close to each other. So now I have mapped this. I can actually map this whole metric space that is given to me to this Euclidean space E. To this, there are points on these blue curves, and these blue curves are considered now as a point cloud. I use the first result where I want to interpolate points in Euclidean space to a smooth surface. I construct the surface M that is here, and we have also the orthogonal projection close to this red smooth surface. So what we do, we apply this surface interpolation algorithm that we earlier described, union of all these images of the disks to obtain a smooth surface, and then we construct the normal projector to the surface M. So we project the point to closest possible point of M. Now this gives to us the topologically the manifold. Then we have to construct the metric there. Actually, the coordinates is also to be constructed, but let's forget that. Let us consider the metric tensor. We have this Euclidean disk of Euclidean space. Let's take the Euclidean metric there and push the metric forward with composition of this embedding F and the orthogonal projector sigma M. Let me go back to the picture. So here we have Euclidean metric. We push the metric first forward to this blue sets, and then we push the metric forward to the red submanifold of Euclidean space E. And then locally we have very nice metric tensors. Then we just glue them together by using some partition of unity by taking a smooth convex combination of the metric tensors. And then we get a nice metric on the surface M. And this turns out to be the surface that approximates the smooth surface, and the smooth metric on it that satisfies the requirements of the theorems. So that these were the requirements that the Gromov-Hausdorff distance of the data set and the smooth manifold is small, and the sectional curvature is bounded. So this was the algorithm. Also, we have constructive algorithms when we have in the case when we have Gaussian errors. Let me now move to the field that is my main field. Those are the inverse problems for different partial differential equations. How we could use these results in practical problems when we do imaging, and what type of imaging problems we are interested in. So here is the paradigm problem. We are looking for the structure of soil. We are looking for oil or minerals or something like that. And for instance, on the sea, there are ships that do the following type of measurements. They are so-called air guns that actually produce very heavy, very large acoustic signals. The acoustic signal is propagating to the medium. Some portion of it reflects, and then it is measured by microphones that are here. So we have sources close to the surface of the sea, close to the boundary, and then we measure the waves close to the boundary. And we want to find out what is the wave speed here at different locations. If we know the wave speed, then we know lots of information what is the material here. So from this kind of measurements, sources for wave equation and measuring the values of solutions of wave equations, we want to find out what is the Riemannian metric that gives the wave speed here in the medium. This is very much also used in medical imaging. So what is the mathematical model? Let us consider a compact manifold now with boundary M, and then we consider the wave equation, where wave equation is given by the Laplacian that corresponds to Riemannian metric G. The Riemannian metric G gives the travel time. The distances in this metric are travel times between points. So that's how we consider physical medium, that we are not actually considering it like density and elastic parameters. We just consider there's some Riemannian metric, and the Riemannian metric gives travel times in seconds, at how long time it goes from one point to another point when the waves travel along the shortest possible route. Okay, so on the so let nu be the normal vector, and on the boundary we say that the normal derivative of the solution is f, and also the wave vanishes at early time moments. Physically, this f, the normal boundary value, this is physical source. This corresponds to these air guns that produce acoustic signal. Then the U here is related to acoustic pressure that we can measure. So our data that is given to us, that is the boundary where we do measurements. And on a boundary, we are given the Neumann to Dirichlet map that maps the Neumann data of the solution, F, to Dirichlet data of the solution. Or physically speaking, this is said that the boundary source F is mapped to the value of the wave at the boundary. This is the data that is given to us, and what we want to find out, we want to find out what is metric G. Or we actually want to make images of G in local coordinates. Here are some classical results. The so-called boundary control method that was developed in the 80s, and that became somehow very strong method when there was Tatarov's unique continuous result for wave equation that make it work in class of Riemannian metrics. Bosi and Kurylev studied on early 90s on this manifolds. Recently, we have been working on partial data problems, and there also are a new method that is based on focusing of waves that Martin de Hoop and Kepler from Rice and Lauri Oksanen from University of Helsinki, they were able to develop this so much that you can actually implement this numerically. So how this is related to this manifold learning. So first, I will have to somehow take some other results. We showed with Dahl and Kirpich-Nugova that if we are given the boundary data, then we can focus waves. What focusing of waves means. Let's take any point Z on the boundary, and let's shoot a normal geodesic from this point to normal direction and go distance S into the manifold. So the distance of, we assume the distance of 1. So this is not very long, so it doesn't hit to the other part of the boundary, for instance. So we assume that this is valid. Then by using the data that is given to us, the boundary and the source-to-solution map, then we can constructively find boundary sources such that the waves corresponding to these boundary sources, they are such that when the index n goes to large, then the values of the wave, they converge towards delta distribution, and the time derivative converges to 0. So what this means, we can specify a single point inside the manifold, and then we can construct some waves such that at time t capital, the waves concentrate all their energy to a single point. So this is how this is used in applications. For instance, in medical treatments, in there's so-called like bloodless surgery where you use heat to heat for instance cancer so much that the cancerous tissue dies. So do you want to focus the energy of ultrasound so that the focused ultrasound, some portion of it absorbs and produces heat that kills the tissue. Here is this type of numerical simulation that at given time t, the wave is concentrated at the single point. Here actually in Finland, unfortunately, we are not vegetarians here. So there was somehow younger researchers actually were playing with the beef. They made a stick that they called inverse problem researchers beef. That was well done in the middle of the beef and rare outside. So only the chunk of beef was heated. But that is very useful if you want to destroy cancerous tissue in the area where surgery is difficult. That's what they actually do in reality now in medical treatments. So how this is related to the manifold learning? So with Bingham, Kurylev, and Siltanen, we showed that there was a very simple procedure that was basically iterative method where we send waves into the medium, measure what comes out, modify it a little bit, send the wave again, measure and what comes out, and all the time we are doing time reversal and some other simple operations. Then we are able to concentrate waves to a single point at given time. So when we have concentrated waves to say this to one point here, then when we look at the measurements of the waves at later time moments, the wave, if we consider, for instance, this point here, when we have focused the wave at a single point, then the wave propagates back to the boundary, and we can measure how long time it takes to come to different boundary points. So we can measure, we can obtain, when we do the focusing with all interior points, then we get the collection of boundary distance functions. They actually are unfortunately only on non-indexed family, but anyway, we get this kind of family of functions, Rx, where x varies through points of the manifold, and those are the distances from this point x to different boundary points. So I recall that this can be done by focusing wave to some unknown interior point of the manifold, and then looking how long it takes that this focused wave propagates back to the boundary. This gives, in the travel time metric, this gives the boundary distance function. So distances from the interior to the boundary points. Then when we are let's now assume that we are approximately given the collection of all boundary distance functions. Then with Katsuda and Kurylev, we showed that if we are given a set of continuous functions, sorry, here should be, in this context, here should be a boundary of the manifold. So if we are given a collection of functions, which Hausdorff distance in space of continuous functions is to true set of boundary distance functions is less than epsilon, then we can construct a metric space such that the metric space has Gromov-Hausdorff distance to the original manifold, that is constant times epsilon to power 1/36, where this epsilon is the error in the data. So let me put this a little bit together, and I explain this, the recent result, what type of stable construction results, and they give to inverse problems. And we put this all together by using the inverse spectral problem, or actually the inverse interior spectral problem. It's the following. Let us assume that we have a manifold M, compact manifold M with metric G, and then we consider the eigenvalues lambda j and orthonormal eigenfunctions that satisfy this equation on the manifold. Let's assume that we do measurements in some ball B. So here is in this picture we consider torus, and the torus has a small ball in the surface of the torus. So this is just ball B. So we assume that we are given the ball, this ball here, where we do measurements. Then we measure all eigenvalues, and then we measure the restrictions of eigenfunctions for this ball. And our aim is to determine the isometry type of the manifold, that is the topology and the differential structure and the Riemannian metric of this manifold. So we want to somehow see that the manifold really makes a. So what type of results one can prove when one combines all these results? With Bosi and Kurylev, we proved that if we are given the dimension of the manifold, bounds for the curvature, diameter, injectivity radius, and the ball of the radius where we do measurements, then there are some parameters such that the following is true. Following is the following. So if the errors in the data are small enough, then if we are given two Riemannian manifolds, such that the three derivatives of the Ricci curvature is bounded, the diameter is bounded, the injectivity radius is bounded, and then to formulate the problem, let us identify the balls of these manifolds with balls in Rn using normal coordinates. So we assume that we are in this picture, and we consider local coordinates in this ball. So if the metric tensors in the ball are close to each other, and if all eigenvalues that satisfy the property that eigenvalue is smaller than 1/delta, if all these such eigenvalues are close to each other, and if all restrictions of the eigenfunctions on these two manifolds restricted to this ball is smaller than delta, then we can construct a metric space M with some discrete metric, such that the Gromov-Hausdorff distance of the original manifold and the constructed manifold, so the constructed metric space is bounded. Unfortunately, the bound is at this moment is not very good, but anyway, there is some stability estimate. Now, when we have constructed a discrete metric space M star that has this property, then we can use these results that I described, these manifold learning results, for instance, this Fefferman, Ivanov, Kurylev, Narayanan result that I described, to construct a smooth manifold that approximates this metric space M star. In this way, we can construct a smooth manifold from the data. So please.
If the eigenfunctions have multiplicity, do you have to change the form of this condition somehow?
That is a very excellent question. Yes. So yes. So this is so actually. So if this is true, then if the assumptions are true, then the result is true. But you can formulate this in a more in different way, in a way that so if you have eigenspaces that has higher multiplicity, then you allow that you pre-process your data by, for instance, by making orthogonal rotation to the eigenfunctions. And there is also a little bit what is the natural way to say that when this was a simplification. This is true that if this is holds, then you can construct a metric space. But you could ask, does this make sense? Is this condition I stable? And to make this stable in small perturbations, you actually have to consider also the case that if you have eigenvalues that are very close to each other, then you take the all eigenfunctions in that is the span of two eigenspaces, and then you can mix information there, because in practice you cannot separate eigenfunctions where the eigenvalues are extremely close to each other. In practice they look the same. So you have to look clusters of eigenvalues corresponding corresponding spans of eigenfunctions, and there you are allowed to do orthonormal rotations. Yeah, so you can improve this result so that it makes better sense from practical point of view. Actually, this was the whole story. I wanted to thank you and for your interest to point clouds. Thank you very much.
Thank you, Matti, for a wonderful talk. Are there any more questions?
So at some point you spoke about some Gaussian perturbations. Can you comment about what
Yes.
kind of results do you get?
Yes. Yeah. Yes, I mentioned it very, very, very quickly. Yeah. So the results that we have in this we have published in the Science Journal of Data Science. There we assume that we have some smooth manifold N, and then we choose a subset of it by random sampling. That we take randomly sampled points, and for all the randomly sampled points, we imitate this. Okay, put it in simple terms, that we take we consider all points in this randomly sampled set. Then we measure the distances of these points and add their random errors. And actually, this type of data, when we have lots of sample points, then we can recognize which points are close to each other. We can start to average the data so that the Gaussian random errors with large probability, when they are averaged, they become very small errors, and then we can apply this result. So this is possible to do that when we have a manifold, we take lots of sample points and measure the distances, even if the errors in the distances are large, but they have a known distribution. Then we can start to do averaging to produce the corrected distances in slightly smaller sample set.
I see. So it's eventually, so this averaging trick that you spoke about, and then using this result, is that?
That's what we have to do, yeah.
Okay. Thank you.
Thank you very much.
So, are there any other questions? So, if not, we'll thank Matti. Thank you.
Thank you very much. It was really a pleasure to give, and I have to say that I have to follow in future also. Your seminar seems to be very interesting.
Thank you.
Yeah, thank you very much for interest.
Thank you.